Welcome everybody. So today we are going to discuss about how to analyze a given frame by stiffness method. So in the previous classes we have already discussed how to analyze beams. So if you are given a beam with a single degree of freedom or 2 degrees of freedom or 3 degrees of freedom, you all know how to analyze a beam. And we have also seen two problems on frames. So in all those two previous problems, your frame did not have any sway. But in this problem, see, because the lengths of the columns are not unique, the lengths are different, it will have sway. Also, see, I will read the given question. So the given question is analyze the given frame by stiffness method. So this is your given frame. We will take this fixed end as A, this as B, C and D. And the column AB is 4 meter of span length. The beam BC is also 4 meter span length. But the CD is 6 meter of span length. So this CD is greater than AB. So because of the unequal lengths of the columns, you will have a sway. So now you all know what is a sway and what are the reasons for the occurrence of sway in frames. We have already discussed this in our previous classes. So also it is given a 10 kilonewton load is acting at B. Okay, so this 10 kilonewton load is acting at the joint B. So because of this load, so we have two reasons here for the occurrence of sway. One is the column is of uneven lengths and another reason is this 10 kilonewton load acting at the joint B, acting horizontally at the joint B. So these two are the reasons for the occurrence of sway here. But there will be only one sway, right? So how the sway occurs, you all know. So because of this load, your frame will be, see, this frame will be moving like this. Okay. So if when the frame is moving like this, see, this beam gets shifted towards here. So there is no change in the length of the beam. This beam will be just shifting towards the right. But the columns will show an increase in length. This will yield. This column will yield. So this will yield to some deflection delta in the horizontal direction. So since load is acting, 10 kilonewton load is acting at the joint B in the right direction, you will have the displacement towards the right. Okay. So now we will move on to solve our problem in a step-by-step manner. Okay, so as you all know, as we have all discussed in our previous classes, our first step in analyzing a given structure, in analyzing a given system by stiffness method is determination of kinematic indeterminacy. Okay, so step 1 is kinematic indeterminacy or degrees of rotation. So kinematic indeterminacy, also known as degrees of freedom. So we all know what is kinematic indeterminacy. It is the number of independent displacement coordinates. So if we see here, the independent displacement coordinates are the rotation at B, rotation at C, and the deflection at B, that is the sway moment. The deflection at B because of sway. So our kinematic indeterminacy is 3. So the degree of kinematic indeterminacy is 3. That is, we have a rotation at B, we have a rotation at C, and we have a sway. That is, as I explained to you earlier, this beam shifts towards the right and the columns gets yielded or deflected towards the right. So that is sway. So we have one sway displacement, that is one deflection displacement and two rotation displacements. Okay, so kinematic indeterminacy is 3. Now, step 2, we shall move on to step 2. So, as we all know, step 2 is determining the force matrix. Force matrix, it will be represented by capital R. So, what are the forces responsible for this displacements? What are the forces responsible for this independent displacements? That is our force matrix. So, in the previous classes we have discussed the procedure is we will find the fixed end moments, and from fixed end moments we will determine the equivalent joint loads. From the equivalent joint loads we will determine the forces corresponding or forces corresponding to the displacements, corresponding to the independent displacements. That is forces corresponding to theta B, that is moment at B, force corresponding to responsible for theta C, that is moment at C, and the sway, that is the force acting at B. Okay, so these are the three external loads and moments responsible for your force matrix. But in this case, see, first step is we have to determine the fixed end moments. But in this case, there is no fixed end moments because the load is acting, the force is acting at the joint. So we will have fixed end moment if the force is acting at any of the intermediate span, at any points in the span other than the joints. So in that case only we will be having fixed end moments. So here we don't have fixed end moments, right? So we have a 10 kilonewton load acting at the joint. So directly you can write the force matrix, right? So our force matrix is, so we have 3 degrees of kinematic indeterminacy. So we can take the order as like this. That is, this 10 kilonewton load is responsible for this sway. So that we will take as our first system ordinate. So second system ordinate can be the rotation at B, and the third system ordinate can be a rotation at C. So our force matrix R will be, that is, first we will consider this as sway, that is the load responsible for sway, that is 10 kilonewton. And if there is a rotation at B, we have to consider a moment at B. So here we don't have a moment at B. So we will take moment at B equal to 0. Here we have theta C, that is rotation at C, but we don't have a moment at C. So we will take moment at C also will be equal to 0. So this is our force matrix. Okay, that is our P is 10 kilonewton. Our moment at B will be equal to 0 and moment at C also equal to 0. This is how you got 10, 0, 0. Okay, now we will move on to step 3. So you all know step 3 we will be writing or we will be representing the system coordinates. So step 3 is system coordinates. So system coordinates, we will represent it as a small r, right? So for our frame, so frame is like this. So we have the system coordinates corresponding to our force matrix. So first one is the P force. So this we will take as R1, that is our first system coordinate. Second is MB equal to 0. So we will give a clockwise moment at B. So we will give a clockwise moment at B. So this can be taken as a second system ordinate. Next is MC. So we will give a clockwise moment at C. That is our third system coordinate. So our system coordinates are R1, R2 and R3. Now we will move on to step 4. So step 4, we will be representing the element coordinates. So we all know if we have 3 elements, we will have 6 element coordinates, each at one end, right? So our element coordinates can be represented like this. So system coordinates will be represented by small r. Element coordinates can be represented by small q. So our element coordinates also we will assume, initially we will assume clockwise rotation, right? Clockwise moments. So in AB, along these column, that is along the element AB, we have the element coordinates as q1, here a clockwise moment, q2, and in the element BC, we have a clockwise moment q3, a clockwise moment q4. Along the column CD, we have clockwise moments q6 and a clockwise moment of this is q5. This is q5 and this is q6. So now we will move on to our step 5. So step 5 is the determination of displacement transformation matrix. Very important, right? Displacement transformation matrix. So the symbol for displacement transformation matrix is beta. So how will we determine the displacement transformation matrix? We will be applying unit load along the not unit load, it is unit displacement. We will be applying unit displacement along the system coordinates R1, R2 and R3. Right? So, applying unit displacements. So here what are our unit displacements? Displacement corresponding to R1 is delta B, that is displacement at B. Displacement corresponding to R2 is the rotation at B. Displacement corresponding to R3 is the rotation at Z. So we will give the displacement at B, unit displacements, that is displacement at B is equal to 1. Displacement at, this deflection at B equal to 1. The next displacement, that is rotation at B equal to 1. And rotation at C is equal to 1 along the system coordinates separately, right? Along the system coordinates separately. So we have 3 system coordinates. We have to apply 3 times, right? We have to apply 3 times the unit displacement. So first time when we are applying the unit displacement, so our first unit displacement is delta B. So we will draw all the 3 cases. So first case you will be applying delta B equal to 1, right? So here, you can apply delta B is equal to 1. So this much, okay? So this column will be displaced here. So similarly, this beam will be displaced. So you will have delta B is equal to 1. This delta B is equal to 1. Here also delta B is equal to 1. Now, because of this delta B, what is the rotation? So here you will be applying theta B is equal to 1 and here theta C is equal to 1, right? Now, here when you are applying delta B is equal to 1, what is the rotation? at A, B, C and D. So your rotation components will be, so this you can take it as theta 1. So here this is theta 1 at A, right? And here also our rotation will be, you can take this as theta 2. So this will be equal to theta 2. You take the clockwise rotation. Sorry. See here, this is from the beam, from the column. See, your column is displacing like this. So from the column, your rotation is anti-clockwise. Here from the column, this is, okay, now this is your column. So from the column, your rotation is anti-clockwise. So the direction is very important. Here from the column, your rotation is anti-clockwise. Here from the column, your rotation is anti-clockwise. So everywhere it is anti-clockwise. Okay. So now, what is theta 1? So we take tan theta 1 is equal to, we know tan theta 1 is equal to opposite side by adjacent side. So opposite side is 1, delta B, that is 1 by, this is the adjacent side. Adjacent side, we know this is 4 meter, right? The span is 4 meter. So it is 1 by 4. We take tan theta 1 is equal to small, from which we get theta 1 is equal to 1 by 4. That is, rotation at A is 1 by 4, rotation at B is 1 by 4. Since the direction is anti-clockwise, it will be minus 1 by 4 when we are taking the beta matrix. Now, here also it has displaced to 1. So we will find tan theta 2. So our tan theta 2 will be equal to 1 by, this is a 6 meter, right? This is 6 meter. So this is 1 by 6. So we get theta 2 is equal to 1 by 6. We take tan theta 2 is small. We assume tan theta 2 is small. So theta 2 is equal to 1 by 6. Now we will apply unit rotation at B. That is our second case, right? Theta B is equal to 1. So this is our B. This point is B. So when you are applying theta B is equal to 1, you are applying a clockwise rotation, right? So here the positive displacement delta B is equal to 1. Here the clockwise rotation theta B is equal to 1. So when you are applying a clockwise rotation at B, your span will be rotating like this, right? At B, and this span will be rotating like this in the clockwise direction. So your displacement will be like this. So here the displacement will be like this. Okay. So this is our clockwise. So this is clockwise rotation, and here also this is clockwise rotation. So you get theta B is equal to 1, and here theta B is equal to 1. Now we will be applying unit rotation at C. So at C, this point, this joint is a C. So at C, when you apply a clockwise rotation from here, this span will rotate like this, and this span will rotate clockwise rotation, right? So it is like this. So your displacement because of this rotation will be like this, and the displacement because of this rotation will be like this. So here theta C is equal to 1, and here also your theta C is equal to 1. Now we will write the beta matrix. So we get our force displacement matrix, that is so our beta matrix, that is force displacement matrix, will be equal to, so for the first case, that is when delta B is equal to 1, this is anti-clockwise, anti-clockwise, anti-clockwise and anti-clockwise. So it is minus 1, sorry, theta 1 is 1 by 4, right? So minus 1 by 4, minus 1 by 4. In the beams, you don't have any rotation because of rotation because of this displacement. So your beta matrix will be 1 by 4, 1 by 4, 0, 0, then theta 2, theta 2. That is minus 1 by 6, minus 1 by 6. Here also it is minus 1 by 4, minus 1 by 4 because it is anti-clockwise. So it is minus 1 by 4, minus 1 by 4, 0, 0, minus 1 by 6, minus 1 by 6. Now for the second case, theta b is equal to 1. So here theta is 0. So 0, 1, 1, 0, 0, 0. Here it is clockwise rotation, so positive, right? So 0, 1, 1, 0, 0, 0. Now when you are applying theta c is equal to 1, clockwise rotations. So 0, 0, 0, 1, 1, 0. 0, 0, 0, 1, 1, 0. So now we have obtained our beta matrix in step. So this was our step 5. Now we will move on to step 6. Okay. So step 6 is element stiffness matrix, which is also known as assembled stiffness matrix. So element or assembled stiffness matrix. So we all know this is element stiffness matrix because we are taking the stiffness for the elements, and we know, and this is represented by element stiffness matrix is represented by small k. And this is called assembled stiffness matrix because you have to determine the element stiffness matrix separately and then we will be assembling this. So this, we know the element stiffness matrix small k will be equal to EI by L into 4, 2, 2, 4. So now we have three elements AB, BC and CD. So for all the three elements, we have to find EI by L. We have to find the element stiffness matrix. So we know this for AB and BC, L remains constant, E remains constant, I remains constant. So for AB and BC, your element stiffness matrix will be same because same length. But for CD, it is different because the length is different, 6 meter. So we will write for AB and BC, that is K1 and K2, we will write K1 is equal to K2, and for K3 we will write it separately. So for K3, L is 6 meter. So we will write K1 equal to K2 is equal to EI by L. So L is 4 meter. So 4, 2, 2, 4. Now what about K3? So K3 is equal to EI by L. L is 6 meter into 4, 2, 2, 4. So we will we will take EI out. Okay. So EI is common for both. So for K1 is equal to K2, we will take EI into 4 by 4 is 1, 2 by 4 is 0.5. So 1, 0.5, 0.5, 1. For K3, we will divide it by 6. So we get EI into 0.67, 0.33, 0.33, 0.67. Okay, so now we will assemble the element stiffness matrices. So when we are assembling, how do we assemble? Our K matrix will be equal to K1 matrix, K2 matrix. It will be a diagonal matrix, right? K3 matrix. So the diagonal matrix and all the remaining terms will be 0. So we get our K matrix as EI is common. So EI into first K1 is 1, 0.5, 0.5, 1. All the remaining terms are 0. So for K2 matrix is also same. So for first element it will be 0, only for second element, that is 1, 0 0.5, 0 0.5 and 1. For third element, EI we have taken out, remaining is, so sorry, here it is 0, 0, 0, 0. And for the third element, 0.67, 0.33. So 0, 0, 0, 0, 0, 0, 0, 0, 0.67, 0.33, 0.33, 0.67. So this is our element stiffness matrix, small k, right? Now we will move on to our step 7. So step 7, we have to determine the system stiffness matrix. So system stiffness matrix, as you all know, the symbol for system stiffness matrix is capital K. Right? Capital K. And we know capital K is equal to beta transpose small k into beta. So we get our capital K, that is the system stiffness matrix, as we write beta transpose, we will interchange rows and columns. So we get minus 1 by 4, minus 1 by 4, 0, 0, minus 1 by 6, minus 1 by 6, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0 into small k matrix. So what is small k matrix? We have found it in our previous step, that is small k matrix is EI into 1, 0 0.5, 0 0.5, 0, 0, 0, 0, 0. Sorry, this is not 0, this is 1. So 0, 0, 0, 0, 0, 0, 0, 0. And for the second also it is 1, 0 0.5, 0 0.5, 1, 0, 0, 0, 0. For the third element, that is 0, 0, 0, 0, 0, 0, 0, 0, 0 0.67, 0 0.33, 0 0.67, 0 0.33 into beta matrix, right? So our beta matrix is minus 1 by 4, 0, 0, minus 1 by 4, 1, 0. Here it is 0, 0, 1, minus 1 by 6, minus 1 by 6. Here it is 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0. Okay. So now we will solve this K matrix. So when you solve this K matrix, you will get this is equal to this matrix, that is minus 1 by 4, minus 1 by 4, 0, 0, minus 1 by 6, minus 1 by 6, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0 into, so multiplying these both, that is K and beta, you get When we solve these both, by multiplying these both, we will get EI into 1 minus 1.5 by 4, 0 0.5, 0, minus 1.5 by 4, 1, 0, 0, 1, 0 0.5, 0, 0 0.5, 1, minus 1 by 6, 0, 0 0.67, minus 1 by 6, 0, plus 0 0.33. Now, multiplying these both, we will get so multiplying these both, we get our K, capital K matrix as EI into, see this is 3 cross 6 and 6 cross 3. So finally you will get 3 cross 3 matrix. So you get EI into 0 0.243 minus 0 0.375 minus 0 0.166 minus 0 0.375 to 0 0.5 minus 0 0.166 0 0.5 1.67. Okay, so now we will move on to, so this is our step 7, determination of system stiffness matrix, right? Step 7, determining the system stiffness matrix. Now we will move on to step 8. So step 8, we have to determine, say this, that is system stiffness matrix, capital K. We are moving on to step 8. Step 8 is system displacement matrix. System displacement matrix. Okay, so we know the symbol for system displacement matrix is a small r. So that is equal to capital K inverse into capital R. So what is capital K inverse? Inverse of this matrix. So this is a 3 cross 3 matrix, right? 3 cross 3 matrix. So how will you determine the inverse of a 3 cross 3 matrix? You can find the inverse directly by using your calculator. It is very simple, right? If not, the procedure is, I will tell you the procedure for this problem for a 3 cross 3 matrix. So finding K inverse, right? So capital K inverse will be equal to 1 by determinant of K. Determinant of K matrix into, it is a matrix of cofactors of K transpose. That is, see, you have to determine K matrix, determinant of K. You have to take the K transpose, then find the cofactors of all the elements in K transpose. That is your K inverse matrix. Okay. So I will just explain you for this problem. So for this K inverse is equal to, for this problem, how will you get K inverse? See, we have here 1 by EI, right? We have EI. So I am writing 1 by EI. 1 by EI. So when taking the inverse, this constant, you have to divide it, right? So 1 by EI into this. That is 1 by determinant of K into matrix of cofactors of K transpose. Now, how will you determine the determination of K matrix? So, determination of K matrix is this value multiplied by determinant of this minus this value into determinant of the cofactors, that is this and this, right? Plus this value into determinant of this. So plus, minus, plus. So what you get is 0.243, this is determinant of k, okay, into determinant of, this is the cofactors. Cofactors alla, the determinant of the other, you cancel the rows and columns, that is 0.243, you cut and this. So the remaining terms 2, 0.5, 0.5, 1.67. When you are taking 0.375, so these 4 terms will come. When you are taking this, these terms will be coming. Okay. So it is 2, 0.5, 0.5, 1.67 minus, the next term is minus 0.375 into determinant of 0.375, 0.5 minus 0.166, 1.67 plus 0.166 into determinant of minus 0.375 to minus 0.166.5. Okay, so you can find the value. You can find what is determinant of k. Now you have to find, so determinant of k is over. Now you have to determine the matrix of cofactors of k transpose. Remember, matrix of cofactors of k transpose. So we will find k transpose first. So how will you find k transpose? Just interchange the rows and columns, right? So interchanging the rows and columns, you will get your k transpose as 0.243 minus 0.375 minus 0.166 minus 0.375 to 0.5 minus 0.166, 0.5, 1.67. So now we will find the matrix of cofactors of K transpose. Okay. So matrix of cofactors of K transpose is equal to, so it is matrix, right? So first one is cofactor of this value, cofactor of first coefficient, that is cofactor of 0.243 is plus determinant of, you can cancel these both, so you get 2, 0.5, 0.5, 1.67, 2, 0.5, 0.5, 1.67. Okay. Now cofactor of the second value, that is cofactor of minus 0.375. So the cofactor, so first we have taken positive, for the next the cofactor value, the sign will be minus. So minus of, so these 4, determinant of these 4 values, that is minus 0.375, 0.5, minus 0.166 and 1.67. So you get determinant of minus 0.375, 0.5, minus 0.166 and 1.67. Now for the third case, third is this, right? So for this you will be getting, so for that you have to take these 4. Okay. So as such you can take for all the values. Next will be for this 0.375, next will be 2, next will be for 0.5, etc. So what you get here is plus See, once you have taken plus, then minus, then plus. Then for the next row, it will start from minus. If you have started the first row from plus, next will be minus. Okay. So here plus, minus, plus. So plus of minus 0.375 to minus 0.166, 0.5. Okay. Now for this value, the cofactor will be minus 0.375, minus 0.166, 0.5, 1.67. Now plus 0.243, minus 0.166, minus 0.166, 1.67. For next term, it is minus. Okay, I am not proceeding with the other things. So this is the procedure, right? So here you will get plus determinant, minus the determinant, and plus determinant. So this is the matrix. So this matrix is matrix of cofactors of K transpose, right? So finally what you get is your K inverse will be, so you can calculate if you have time, otherwise you use your calculator, right? So that easily you can complete this. So otherwise it is a time consuming process. Please don't do it. Please don't calculate. You use your calculator. So K inverse is equal to, you will get K inverse is equal to 1 by EI into 5.919, 1.0408, 0.2768, 1.0408, 0.7234, minus 0.1131, 0.2768, minus 0.1131, 0.6608. Now, this is our step 8, right? Now we will find what is system displacement matrix. System displacement is small r, that is capital K inverse into capital R. So our small r, that is system displacement, so small r is equal to K inverse. Okay, so I will write here, that will be easy for me. So r is equal to K inverse into capital R. So this is K inverse. Capital R is 1 by EI into, we have already calculated capital R. So it is so where have we calculated capital R? The first step, right? Okay, this that is our force matrix 10 0 0. So small r is equal to capital R into, sorry, I have written it wrongly. Capital R is 10 0 0. So that you will get your small r as 1 by EI into 59.2035, 10.4085, 2.7685. Okay. So step 8 is over. We have determined the system displacements. Now we will determine the element displacements. That is our step 9. Okay. So step 9 is element displacement. Element displacement is represented by small q. So small q is equal to beta into small r. That is system displacement. Beta is displacement transformation matrix. Displacement transformation matrix, that is the relationship between the displacements, element displacements and system displacements. Element displacements is q, system displacements is r. So you will get your element displacement small q as the value for beta is minus 0.25, that is 1 by 4, right? Minus 1 by 4. So it is minus 0.25 minus 0.25, 0, 0, that 1 by 6 we will take it as 0.166. So it is minus 0.166 minus 0.166, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0. Multiplied by small r. Small r is 1 by EI into 59.2035, 10.4085, 2.7685. So you get 1 by EI into minus 14.8 minus 4.392, 10.408, 2.76, minus 7.059 and minus 9.827. We will move on to our step 10. So step 10 is the final steps, right? That is element forces. So element forces is represented by capital Q. So capital Q is equal to element stiffness small k into element displacements small q. So your capital Q, that is element forces, will be equal to small k is EI into 1, 0.5, 0.5, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0.5, 0.5, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0.5, 0.5, 1 into multiplied by small q, that is element displacement. Small q is, we have found it as 1 by EI into minus 14.8 minus 4.392, 10.408, 2.76 minus 7.059 minus 9.827. So you will get the system forces capital Q as minus 16.995 minus 11.79, 11.79, 7.96, sorry, minus 7 point, sorry, plus 7.96, minus 7.96 and minus 8.916. See, now we will write the total forces. Last step, step 11. So step 11 is our total forces. So total forces is equal to capital Q plus fixed end moment. That is element forces plus fixed end moments. Now for this problem we don't have fixed end moments because there are no loads acting on the span. The load is acting only at the joint. So we don't have fixed end moments. So our fixed end moment is 0. So for this case our total force is equal to system forces capital Q. Now we will draw the bending moment diagram for our frame. So our bending moment diagram will be like this. So we all know this is our frame, right? So our frame is like this. So this is A, B, C and D. Now this is the first Q1, right? This is Q1. So our Q1 is minus 16.995. If it is minus, it is anti-clockwise, right? So you draw this anti-clockwise moment from outwards. So it is pointing towards the left. So 16.995 in our bending moment diagram, we will mark the bending moment as that is 16.995 kilonewton meter. Then the second one, that is in the span AB at the joint B, it is minus 11.79. So again anti-clockwise towards the right. So it is here it is 11.79 kilonewton meter. Okay. So this is for AB. Now for BC. So for BC, when we take BC, it is plus 11.79. So it is clockwise, right? Clockwise, acting downwards. So plus 11.79. 79 kilonewton meter. Here it is plus 7.96 clockwise, right? So upwards. So here it is like this, 7.96 kilonewton meter. So while drawing the bending moment diagram, it will be coming like this. Now this is for CD. Now when you take CD, it is minus 7.96. So anti-clockwise towards the right. So minus 7.96 kilonewton meter. And here at D, it is minus 8.916. Again anti-clockwise towards the left. So here it is 8.916 kilonewton meter. Okay, so this is the bending moment diagram for our given frame. Okay, that's all. Thank you for listening. So hope you all understood. We will see the next problem in the next class. Okay, thank you.